torque due to magnetic force on a current-carrying loop. Consider a rectangular loop PQRS of length L and width W, suspended perpendicular to a uniform magnetic field B bar. Current I flows in the coil in the direction PQRS. On applying Fleming's left-hand rule on side QR, the magnetic force F1 equal to IWB turns out to be perpendicular to QR and to the magnetic field. Magnetic force F2 on SP, that is equal to IWB, turns out to be opposite to F1. As you can see, forces F1 and F2 are equal in magnitude, opposite in direction, and have the same line of action. Hence, the resultant effect on the loop is zero. Similarly, force on PQF3 equal to ILB is same in magnitude, but opposite in direction to that of force F4 on RS. Since the line of action is the same for both forces, they have no effect on the loop. Now, let the loop's normal make an angle theta with the magnetic field. Forces on SP and QR are equal and opposite to each other, and they have the same line of action. Hence, they produce a net force equal to zero and net torque also equal to zero. Magnitude of the force on PQ is equal to the magnitude of force on RS, but they don't have the same line of action. Hence, they produce a couple due to which the coil tends to rotate in the clockwise direction. From triangle PSN, sin theta is equal to Pn by Ps. This gives the distance between the forces Pn equal to W sin theta. Net torque acting on the coil is equal to the product of magnitude of force and the perpendicular distance between the forces. WL is equal to area of the loop. Hence, torque on the coil is equal to IBA sin theta. Let A bar be an area vector of magnitude A normal to the loop. By curling fingers of right hand in the direction of thumb gives the direction of A bar. Net torque can be written as IA bar cross B bar. IA bar can be replaced with a vector called magnetic moment. Magnetic moment of a loop is the product of current and area vector. Torque on a loop is simply M bar cross B bar. This result is valid for loops of all shapes. If the coil has N turns, magnetic moment of the loop is N times IA bar. Summary. Magnetic moment of a loop is the product of current and area vector. Torque on a current